And there are millions of these in every galaxy. They are all over the place. And then we have supermassive black holes, which weigh between 10 to the 5, so 100,000, and 10 to the 10 times the mass of our sun. And these black holes are found at the centers of all relatively big galaxies. So when I talk about black holes today, I'm referring to the supermassive black hole variety that reside at the centers of galaxies. Okay, so we have learned that supermassive black holes are found in the cores of all relatively big galaxies. So by that I mean galaxies roughly the size of our Milky Way and larger. So these are just a few examples of some nearby systems where we have found and weighed supermassive black holes. So all the way on the left there is an image of the orbits of stars at the center of our Milky Way galaxy. So it's pretty amazing. Over the course of a couple of decades, people have tracked the orbits of individual stars at the center of our galaxy, and using that have been able to get a very accurate estimate of the black hole there of about 4 million times of our sun. On the upper right there is the recent image from the Event Telescope of the black hole M87. So this is the shadow of the event horizon. That black hole is much more massive than ours, about 6 billion times the mass of our sun. And then for systems where we can't necessarily do things like measure the orbits of individual stars or directly image the event horizon, we can sometimes look at the motions of stars or gas at the center of the galaxy. So on the bottom right there is another relatively nearby galaxy, NGC 1332. You can see in the Hubble image there a nice dust disk surrounding the black hole at the center of the galaxy. And then the ALMA image there shows the motion of gas at the center, which you can use to estimate the mass of the black hole. There are lots of open questions related to supermassive black holes, and one of the most important ones, I think, is how do supermassive black holes form? So there's a really interesting puzzle in supermassive black hole formation, which is that we see extremely massive black holes in the very early universe. So this figure just shows black hole mass versus time since the Big Bang. And the key takeaway here is that we see black holes as massive as 10 billion times the mass of our sun in less than a billion years after the Big Bang, which is, cosmologically speaking, a very short amount of time. So what we want to understand is how do we get these black holes so big so fast? They either have to start small and grow almost constantly at the maximum possible rate, or they could start off at a bigger size and then we don't need to worry about them growing at the maximum possible rate. And so there are, I'll talk about some different theories for how we think supermassive black holes might form, but this is a really interesting question in the field of supermassive black holes, is how do we get these extremely massive ones so in such a short amount of time. Okay, so this is, roughly speaking, the two kind of main theories for how we think supermassive black holes might form. So they fall into two categories, heavy seeds and light seeds. So these are ways that supermassive black holes might form in the very early universe. So with heavy seed models, you have something like the direct collapse of an extremely massive gas cloud. And this would leave behind an initial black hole with a mass of 10 to the 4 or 10 to the 5 solar masses, so pretty big. And this process requires very specialized and rare conditions. So you wouldn't expect this to occur in every proto-galaxy at high redshift. On the other hand, we have light seed models where the seeds of today's supermassive black holes would form through the deaths of very massive stars in the very early universe. These are called population 3 stars, and they were much more massive than the ones that we observe forming today. And this would leave behind a black hole of initial mass of maybe 100 times the mass of our sun, so much smaller than in the direct collapse model. This would be, might expect this to occur in most proto-galaxies. in the early universe. And interestingly, the population of black holes in small galaxies today can help us distinguish between these different formation scenarios. The plot on the left is just a rough schematic of the black hole occupation fraction, what we expect for the fraction of galaxies that contain a black hole as a function of the galaxy's stellar mass. And the key thing here is that for galaxies with stellar masses above about 10 to the 10 times the mass of our sun, no matter how the first black hole seeds formed, you expect every galaxy to have one today. However, for lower mass galaxies below 10 to the 10 solar masses, if they formed through these light seed models, we expect most small galaxies to contain a black hole, whereas if they formed through heavy seed models, we expect many fewer low-mass galaxies today to contain a supermassive black hole. And we also expect to see differences in the black hole mass versus galaxy stellar mass relation, depending on how these black holes formed. So small galaxies, and in particular, the fraction of small galaxies that contain a massive black hole, can tell us something about how black holes formed in the very early universe. So some of the questions that I'm interested in answering in my work are, what fraction of low-mass galaxies contain a massive black hole? What are the masses of those black holes? And how can we use them to learn about black hole formation and growth? Okay, so hopefully by now I've convinced you that it is worthwhile to search for massive black holes in very small galaxies. They provide constraints on the masses of black hole seeds at high redshift in the early universe, and they are important for understanding black hole formation and growth and the interplay between galaxies and their black holes on all scales. Unfortunately, they are also very difficult to find. So I talked earlier about how we can detect black holes by detecting their influence on the motions of stars and gas around them. The gravitational sphere of influence for a 10 to the 5 solar mass black hole, which is what we expect to observe in these little galaxies, is not resolvable even with our best instrumentation far beyond our local group of galaxies. In some cases, it's not even clear where you would begin to look. So on the upper right there is an image of the Large Magellanic Cloud, which is a dwarf satellite galaxy of our Milky Way. So it's really nearby, but we don't actually know whether the Large Magellanic Cloud contains a black hole. And it's sort of a messy system, so it's unclear necessarily where you would start to look. So as a solution to this, we need to search for accretion signatures of black holes in small galaxies. So that is to say, we need to search for black holes that are consuming lots of material at a very rapid rate. You form a disk of material around the black hole, and lots of light gets emitted from the galaxy center, making it possible to detect the black hole. So on the bottom there is a nearby dwarf galaxy called NGC 4395, and this system happens to have a tiny active black hole of a few times 10 to the 5 times the mass of our sun. So I focus on searching for black holes that are accreting lots of material in small galaxies. So I just wanted to give a little overview of some of the signatures that we look for when we search for active black holes. So on the left there, you have my beautiful artwork of what is called an active galactic nucleus.
One of the best I've ever seen.
Thank you. I made that for my thesis. Yeah. So at the center there, you have your black hole, and there's an accretion disk of material surrounding the black hole, which is feeding it. Optical and ultraviolet photons from the accretion disk ionize surrounding gas in what is called the broad and narrow line regions. And those produce these lines that you see in the spectrum on the right. And the difference between the broad and narrow line region is that the gas in the broad line region is close enough to the black hole to feel its gravitational influence. So you end up with these broadened emission lines because it'll look as if some of the gas is moving towards you and some of it is moving away from you. And so you get these broadened emission lines in the spectrum on the bottom. Whereas gas in the narrow line region still gets ionized as farther out, so you don't get that line broadening. Depending on the viewing angle, you may or may not observe the broadline region. So we think that there is an obscuring torus of material around the black hole. And so if you're viewing the system from the side, you may not see that broadline region, whereas if you're viewing it from the top down, you would see. Okay, and you can also estimate the masses of black holes from optical spectroscopy, which is work that Misty Benz has done a lot on. And so with these broad lines, if you can estimate the distance to this broadline region and how fast those clouds are moving, you can actually get an estimate of the black hole mass. And through a bunch of, from the width of the broad lines, you get the velocity. And then from a bunch of handy correlations, the velocity of those broad lines gives you an estimate of the distance to the broadline region. So the key point here is that just using these broad emission lines, you can get a rough estimate of the black hole mass, which is very powerful. Okay, so up until basically the last 5 to 10 years, we knew of only a handful of dwarf galaxies that contained active galactic nuclei. But thanks to very large-scale surveys where we've observed thousands of galaxies, we've been able to start looking for them in these really large samples. So this diagram on the left is going to come up a lot in the talk, so I'll just take a minute to walk through it. It is called a BPT diagram, which is just the initials of the people who first published it. And what this diagram does is plot the relative strengths of certain emission lines. So on the y-axis, oxygen and H beta, and then on the x-axis, N2 and H alpha. And so it plots the relative strengths of these lines to characterize the dominant source of photoionization in the galaxy. So depending on whether a galaxy is primarily star-forming or has an active galactic nucleus or some combination of the two, the composite, it will fall in a different location on this diagram. So this is a way of finding active galactic nuclei, just using the optical spectra that I talked about. So this particular one is from a study that was done in 2013 by Amy Ryans, where they looked at 25,000 nearby low-mass galaxies with emission lines, and plotted them on this diagram, and found 136 that fell in either the AGN or composite region of this diagram. And so that may not sound like a lot, 136 out of 25,000, but it was actually an order of magnitude increase in the number of galaxies with this mass that we knew to contain an active galactic nucleus. So this was a real step forward in this field. And in my thesis, I actually did some work following up a lot of the galaxies identified through that survey. So one of them is this galaxy RGG 118. The Hubble Space Telescope image is shown on the left there. It's a really nice little spiral galaxy with a stellar mass that is equivalent to that of the Large Magellanic Cloud, the dwarf satellite galaxy of the Milky Way. And these are a few of those optical spectroscopic diagrams that help you determine whether a galaxy has an active galactic nucleus or is star-forming. And so in all of these diagrams just use different emission lines on the x-axis. So using all of these different diagrams, we had narrow emission evidence for an active galactic nucleus in this system. We also obtained follow-up spectroscopy using the MAGE spectrograph on the 6.5 meter Clay telescope at Magellan, and found a nice little broad H-alpha emission line with a width of about 800 kilometers per second. And using that, I was able to estimate a black hole mass of 50,000 solar masses, which for a while was the smallest black hole found in a galaxy nucleus, so the smallest supermassive black hole. In some of the press releases, they called it a supermassive oxymoron. And Chandra X-ray observations also revealed a hard nuclear X-ray point source, which helped further confirm the presence of an active galactic nucleus in this galaxy, and also helped us determine that it was accreting at about 1% of its maximum rate. So it's a really tiny little monster in this pretty typical everyday tiny spiral galaxy. Okay, so these narrow emission line diagrams have been great for finding active galactic nuclei in these small galaxies, but we're also probably missing a large population. So these kind of diagnostics are designed for and calibrated with higher mass galaxies, and there are all sorts of effects that take place for lower mass galaxies that mean you may not select them using those typical diagrams. So that's the same BPT diagram, but what this is showing is how an object's position on the diagram would change with the galaxy metallicity. So as you decrease the metallicity, something that would normally fall in the AGN region instead falls in the star-forming region. You can also have strong star formation, which could dilute the signal from a relatively low luminosity AGN and make it so that you wouldn't detect it with this diagram. And so low galaxy metallicity and star formation dilution are two examples of effects that should primarily affect these low mass galaxies, which mean that we may detect again in these small galaxies using this narrow line diagnostic diagram. So I was interested in exploring what other techniques we could use to find AGN in low mass galaxies. Another great property of active galactic nuclei are that they vary at all wavelengths and on a variety of timescales. So they show aperiodic flux variations at every wavelength that we have observed them at. This is an example of one such variable AGN, very well studied NGC 5548. And so this is just showing the flux from that AGN as a function of time over the span of about 8 years. So you can see that it's highly variable. The amplitude of the variability changes. And this is typically attributed to instabilities in that accretion disk of material that is feeding the black hole. There have been an increasing number of repeat imaging surveys where they take images of the same regions of sky over many years. So there's a lot of surveys where they have publicly available data, and soon there will be the Vera Rubin Observatory Legacy Survey of Space and Time, as it's called now. So there's lots of data to look at this kind of stuff, and I wanted to use optical photometric variability to find AGN in low mass galaxies. So the pilot study for this, I used data from the Sloan Digital Sky Survey Stripe 82. And so this was a survey that the Stripe 82 survey ran from about 1998 to 2008. And they repeatedly imaged this region of sky called Stripe 82. It's about a 300 square degree region shown there on the celestial globe. And the sample of galaxies that I looked at was comprised of 28,000 relatively nearby galaxies, ranging in galaxy stellar mass from about 10 to the 7 to 10 to the 12 solar masses from a catalog called the NASA Sloan Atlas, which is just a really nice catalog of galaxies that all have Sloan Digital Sky Survey spectroscopy and estimated stellar masses. And so I constructed light curves for all 28,000 of these galaxies using data from this survey, and then searched for nuclear variability that was AGN-like. The typical light curve baseline here was about 6 years, with a typical number of data points of 17. I just wanted to give a little overview of the imaging technique. So I'm interested in finding really low levels of variability from an active galactic nucleus that is superposed on top of an underlying host galaxy. And so in order to detect those low levels of variability, we want to subtract off the light from the host galaxy. So we use a technique called difference imaging or image subtraction. to achieve very accurate photometry. So the first step is to create a very high quality template image from the best frames in your set. So the images that have the best seeing and the lowest background. So you combine those to create one really high quality template image. After that, you take an individual exposure and you actually degrade the template image to match the resolution of that particular exposure, and then match the backgrounds as well, and then subtract the template from that exposure. And that leaves you with a difference image, which will be relatively flat, except for anything that happens to be varying between the two images will pop out against the background. So I then take each of those difference images and construct a light curve by measuring the flux in the difference image in a 2.5 arcsecond aperture centered on the galaxy nucleus, as defined in the NASA Sloan Atlas catalog. And then search for AGN-like variability. So this is an example of a galaxy that was not varying. So the plot on the bottom shows the nucleus magnitude, so how much light is coming from the nucleus of the galaxy over time. This particular light curve spans about 2,000 days. The gray points are the actual data, and then the blue line is what's called a damped random walk model. So we want to find objects that are variable, but also variable in a way that we expect AGN to vary. So I'll just show you what this non-variable object looks like first. These are just flashing through the difference images. So not too exciting. And then this is an example of a galaxy that is variable. So the white circle there just shows where we're measuring the nucleus variability. And you can see here very clearly that variability pops out against the background. So again, here, the gray points are the data, and then the blue line is the best fit damped random walk model. And this is a model that describes pretty well AGN variability. So we search for objects that are variable and well described by this damped random walk. And so that's what the blue line is showing, and then the shaded region are the model uncertainties. So this is an example of a galaxy that we found to have AGN-like variability.
I have a question.
Sure.
So did you do this for different filters in to sort of check, as a check on variability?
Yeah, so I just used G-band for this. That was sort of a trade-off between being able to observe higher amplitude variability at bluer wavelengths, and then the fact that the Sloan U-band has very poor signal to noise. So you certainly could go back and redo this with R-band. But since it was a large amount of data, I chose to focus on the G-band for this data set. But you definitely could go back and check with R-band. So from this initial survey, out of this big sample of galaxies, I found 135 that had AGN-like variability, so well described by this damped random walk, 35 of which were in low-mass galaxies. So I'm just showing a couple of examples of low-mass galaxies that were found to have AGN-like variability there on the left. On the right, I'm showing the distribution in stellar masses of the full parent sample in gray, and then of the variable AGN candidates in orange. And so they tend to be more skewed towards higher mass galaxies. Since all of these galaxies had optical spectroscopy from the Sloan Digital Sky Survey, we could explore where they fell on this BPT diagram. So here the points are color-coded by the galaxy stellar mass, where the yellow points are the highest mass galaxies and the purple points are the lowest mass galaxies. And the gray contour just shows the underlying parent population. So what I found was that for the galaxies with variable AGN in relatively massive galaxies, so above 10 to the 10 solar masses, everything that had AGN-like variability also fell in either the active galactic nucleus or composite region of this BPT diagram. However, for low-mass galaxies, the majority of them actually fall in the star-forming region of the BPT diagram. So these are things that have AGN-like variability, but fall in this star-forming region of this diagram, suggesting that these are AGN that would have been missed by this selection technique. So recently, I built on that initial work using a sample, a larger data set from the Palomar Transient Factory. So this is a survey that has covered basically the entire northern sky, so 30,000 square degrees, and took observations between 2009 and 2017. And so here, for my galaxy sample, I wanted to focus on primarily low-mass galaxies, but also included some higher-mass galaxies as well. And so this sample was comprised of about 50,000 primarily low-mass galaxies, and a bit closer of a redshift cut than the previous sample. And so this just shows the area of Stripe 82 relative to the area of the Palomar Transient Factory. And the map there is color-coded by the number of images that were taken for each region of sky. And so the color bar is hard to see, but ranges from 0 to 7,400. So some areas of the sky got a lot of coverage, which is really great. And all of this data is publicly available. So the Palomar Transient Factory sample had 35,000 galaxies below 10 to the 10 solar masses, compared to about 5,000 in the Stripe 82 sample. So this is a big improvement on the sample size. And here the typical light curve baseline was 4 years, and number of points was 70. Out of this sample, I found 250 variability selected low mass AGN. So these are a couple of other examples of these low mass galaxies with AGN that we found through variability. The one on the bottom there is the lowest mass one in our sample at just 5 times 10 to the 7 solar masses. So again, you can see the data there in gray, and then the best fit damped random walk model in blue. Okay, so similar to what I showed with Stripe 82, this is where they fall on the BPT diagram with the points color-coded by galaxy stellar mass. And we see the same thing here, which is that most of the low-mass variability selected AGN would have been missed using this diagram for selection. All right, so using this bigger sample, I wanted to explore how the fraction of variability selected AGN as a function of the galaxy stellar mass. So on the left there, I'm showing the variable AGN fraction versus stellar mass with low mass systems on the left and higher mass systems on the right. The number above each of those points just reflects the number of galaxies in each mass bin. So like I said, we did include some higher mass galaxies, low galaxy stellar masses. However, we also see that the variable AGN fraction is strongly dependent on the apparent magnitude of the nucleus, where we detect more variable AGN in nuclei that have brighter apparent magnitude. So we can, in comparing the variable AGN fraction between high and low mass AGN. Okay, so in order to make a proper comparison, I needed to construct samples that had similar apparent magnitude distributions. So in the plot on the left there, I'm just showing the magnitude distributions of various samples of galaxies. So the gray histogram is showing the apparent magnitude distribution for high mass galaxies. The red histogram is showing the apparent magnitude distribution for galaxies between 10 to the 9 and 10 to the 10 solar masses. And then what I did was draw subsamples from that red histogram that matched the magnitude distribution of the higher mass galaxies, and then measured the variable AGN fraction in those subsamples, so that we were comparing apples to apples, and so comparing the fraction of variable AGN between high and low mass galaxies, matching the magnitude distributions. And so after controlling for magnitude, I find that the fraction of variability selected AGN is constant down to galaxy stellar masses of about 10 to the 9 solar masses. And unless there's some drastic change in AGN variability properties, this suggests that the occupation fraction, so the overall fraction of galaxies that contain a black hole, isn't changing drastically down to galaxy stellar masses of about 10 to the 9 solar masses. I'm not confident in our results below galaxy stellar masses of about 10 to the 9, so our errors are a lot larger there, and we're not sure if our galaxy sample is complete, or what we're not particularly sensitive to detecting variability in those systems, and so we'll need to use more sensitive instruments to really push down below 10 to the 9 solar masses. But at least down to 10 to the 9, the fraction of variability selected AGN is constant. All right, so one of the questions that I'm interested in answering is why are we missing most of the variable low mass AGN using these optical spectroscopic diagrams? So I mentioned that low galaxy metallicity could be one option, or star formation dilution, but comparing the properties of galaxies with variability selected AGN to those selected via other techniques can help us figure that out. So here I'm showing the colors of galaxies, low mass galaxies with AGN selected through variability, and comparing them to galaxies in the same stellar mass range with AGN selected through optical spectroscopy. So the blue histogram are galaxies that I found through variability, and then the purple shows the color distribution of the Rhines 2013 sample of dwarf galaxies with AGN selected through that BPT diagram. And so the key takeaway here is that the galaxies that I find to have variable AGN are bluer than those with AGN found through optical spectroscopy. So this is some evidence for star formation dilution perhaps playing a role for these systems in terms of us not being able to detect their AGN through optical spectroscopy. But there's definitely lots more work to be done here in terms of comparing galaxy properties and measuring metallicities. Okay, so this is a little aside on some other interesting objects that I found through this variability work in comparing light curves for objects where we had data in both Stripe 82 and the Palomar transient factory. So here I'm showing the Stripe 82 light curves in blue. So again, that covered from about 1998 to 2008. And then the Palomar transient factory light curve in gray. So that covered from about 2009 to 2017. And so these are two galaxies that we observed to have AGN variability in Stripe 82. They also had those nice big broad AGN optical spectroscopic emission lines, so broad emission lines and narrow emission line evidence for an AGN. So there was no question that these galaxies had active black holes, and they showed this really strong high amplitude AGN-like variability in Stripe 82. And then when we looked at their light curves with the Palomar transient factory, we didn't see any variability. So we wanted to look and see what was going on with these systems. So we took follow-up observations using Keck, and what I'm showing here on the right is the change in the broad H-alpha emission lines from the earlier Sloan Digital Sky Survey observations in 2000 and 2001, and then the follow-up observations taken in 2019. So we see that these galaxies undergo this change in variability where they go from being variable to not, and it turns out that these galaxies also undergo extreme changes in their broad emission lines where they've significantly faded from 2000 to present day. So the gray is earlier spectroscopy, and then the blue is the newer spectroscopy. And you can see very clearly that between these two observations, the broad lines have faded significantly.
Vivian, are you showing in the bottom left that your laptop is more powerful than all the computers at the telescope?
No, I'm showing the very sad remote observing facility. Yeah, so, that's the top is what you think of when you think of observing at Keck, and then the bottom is what it actually is, which is the basement of the astronomy building at Yale.
How many examples do you have of these kinds of objects?
3 so far, but I'll actually be revisiting that room later this week. So, yeah. So we are beginning to discover these so-called change state AGN in increasing numbers. So these are galaxies where we see these really drastic changes in their broad emission lines on relatively short time scales. So this is less than 20 years. And we don't usually expect to see these kinds of changes on these short time scales, but there's something drastic happening either in terms of accretion properties or obscuration that's causing these changes. And somewhat unexpectedly, about 15% of the variable broadline AGN in the Stripe 82 sample showed this behavior where it goes from being photometrically variable in Stripe 82 to showing no variability in the Palomar transient factory. And then we're following them up now with optical spectroscopy to see if they all show this kind of behavior. So there's additional observations underway, and hopefully those will help us to understand what's actually physically driving these changes, whether something is happening to the accretion disk, or there's some sort of obscuring cloud moving in the way or something like that. Interestingly, we also see objects which go the other way. So they're not variable in Stripe 2, and then they become variable in later observations. And so I'll be really excited to look at those and see if we find the opposite behavior. So going from something where we don't have broad emission lines to systems where we suddenly do see them. But all of these recent repeat imaging surveys have meant that we're finding all sorts of new and unexpected AGN variability behavior. So there's lots of exciting work to be done. Okay, so I'll spend a few minutes now talking about some of the future work that I have planned. So there are lots of existing and upcoming exciting repeat imaging surveys that we can use to expand on some of this work. So this Wiki Transient Facility is similar to PTF. So it uses the same telescope but has a new camera, which has a much wider field of view. So it would be similar type imaging to PTF, but with a much faster cadence. And so we'll be able to expand our baselines there and look for similar type variability. The GALEX time domain surveys have covered about a 40 square degree region of sky. And this looks much deeper, down to about 23rd mag in the UV. And I'm excited to dig into some of that data to search for AGN variability in these low mass galaxies with better sensitivity and at bluer wavelengths. Something that I'm really excited to be pursuing is using data from the Transiting Exoplanet Survey Satellite, or TESS, to search for AGN variability in dwarf galaxies. So TESS has a 30-minute cadence as opposed to observing something every few days, or few weeks. And you would expect that lower mass black holes should have shorter variability timescales. So this is something I'm working on with Krista Smith, who does a lot of AGN variability work using exoplanet satellites. And so we're really excited to see what sort of variability we can detect using this data, and if this will be useful for finding more AGN and dwarf galaxies. Looking forward, the Vera Rubin Observatory Legacy Survey for Space and Time should start in 2023, and this will image the entire visible sky every 3 nights. So there will be a ton of repeat imaging data coming out of this. which will be deeper than Stripe 82 and PTF and ZTF, and so this will be great for doing this kind of work. Then the W first supernova fields, looking more like 10 plus years into higher redshift, provided that W first survives this latest setback. Okay, so we can also improve upon this by adding new samples of galaxies. So one of the things that we're going to want to do is try to select dwarf galaxies based on color where we don't necessarily have spectroscopy, which will be the case for the LSST. We may not have spectroscopy, so we need to work on our selection techniques. I'm interested in exploring the population of AGN in satellite versus field dwarf galaxies to see what sort of factors impact AGN fueling in these smaller systems. We can look at catalogs of merging dwarf galaxies. So an example of a catalog of merging dwarf galaxies, one such object is shown on the bottom left there. And the goal here will be to improve statistics, especially for galaxies with stellar masses below 10 to the 9, so that we can really push down on our estimates of the occupation fraction there. I'm also pursuing a lot of follow-up observations of these low-mass variability selected AGN. So one thing that we're looking at is spatially resolved spectroscopy. So these galaxies all have spectroscopy with the Sloan Digital Sky Survey, which uses a 3 arcsecond fiber. And so what we've been doing is using Keck to take more spatially resolved spectroscopy and see how the narrow emission line ratios change as you move from the outskirts of the galaxy towards the nucleus. So we can isolate emission from the nucleus. And what this is showing is for that particular galaxy, which we found to have AGN-like variability, how the optical emission line ratios change as you move from the outskirts, so those are the points in purple, to the nucleus of the galaxy, which is shown in yellow. And the star there shows the SDSS spectroscopy measurements. And so with Keck, we can see that as you move in towards the galaxy nucleus, the line ratios become more AGN-like, which is another piece of evidence for star formation dilution potentially being the reason that we don't detect these galaxies as AGN using the BPT diagram with Sloan. I also received from some radio observations from the Very Large Array to look for radio emission from these variability selected AGN, and we'll be doing some work with archival Chandra data as well. Finally, with all of these exciting new time domain observations, we're gaining a lot of insight into AGN fueling mechanisms and how AGN accretion disks vary over time. And we're starting to see lots of surprising things like significant fractions of AGN potentially shutting off on timescales of 20 years, turning on. And so with this kind of data, we'll be able to answer questions like, what is the duty cycle for AGN? How long do they turn on for? And is this different between low and high mass galaxies? And explore things like, is AGN growth in low mass galaxies contributed to more by things like tidal disruption events, where you get a star that happens to wander too close to the black hole and gets disrupted, or more typical AGN fueling like in higher mass galaxies, and explore the physical mechanisms that are responsible for these changing state AGN. Okay, so just a few takeaways. We can't observe black holes forming in the very early universe, but clues to the formation of supermassive black holes can be found in today's smallest galaxies. These are traditionally elusive systems and they're hard to find, but variability is a new and very promising way of finding these black holes in small galaxies. And using these results, we can start to place meaningful constraints on the low mass end of the occupation fraction, or the fraction of galaxies that contain black holes. And existing and upcoming time domain surveys, and even further in the future, gravitational wave observatories will improve samples of low mass active galactic nuclei and help us understand black hole fueling and growth on all scales. Thank you for your attention. I'll leave it there.
questions, so why don't we start with a graduate student?
So it seems to me like an important part of this work is how exactly you define what counts as a variable AGN in your samples. So what does well defined by the model mean? Like how are you deciding what gets flagged as variable or not?
Yeah, so basically we model things as a damped random walk, and then depending, using the chi-squared value of the fit to the damped random walk, determine a significance that variability is, that the light curve is better modeled by a damped random walk as compared to non-AGN like variability. And so I pick out things that are more well described by a damped random walk with 2 sigma significance, and then sort through that whole sample. And occasionally we'll get an interloping supernova or something like that, so pull those out by hand.
Were there other cuts in that process, like minimum data points and that sort of thing?
Yeah, so for example, with PTF, we placed a minimum number of data points as, I think it was 20, and that was based on just looking at the scatter in light curves as a function of data points, and then below 20 data points, the scatter was just generally really huge. And we did a similar thing with Stripe 82 data. And then I only used, with Stripe 82, light curves that, images that were classified as photometric, and so there are additional quality cuts that get made in terms of number of data points and things like that. Yeah. Sure.
How were your galaxy stellar masses measured?
So they're measured based on fitting of the 5-band SDSS imaging through the NASA Sloan Atlas. Yeah, so they all have spectra, so we know how far away they are, and then they do some modeling based on the 5-color imaging. Yeah.
Yeah, Russell?
Is there any significant difference in the mass ratio of like stars to gas in dwarf galaxies versus regular galaxies, which could affect maybe the fraction that you see as active?
Ooh, good question. So I don't remember exactly in terms of the fraction, but something that we do observe that's interesting is that for dwarf galaxies, it's basically, we observe almost no isolated dwarf galaxies where star formation has shut off. Almost all isolated dwarf galaxies are star forming, whereas dwarf satellite galaxies are more likely to be quenched through presumably interactions with their more massive host galaxy. And so, I mean, that could definitely play a role in whether we're able to find AGN. But one of the tricky things is that with the AGN selected through optical spectroscopy, those systems do tend to be redder than the general dwarf galaxy population, but we don't know whether we can only observe them through that technique because they're not strongly star forming or something like that. But yeah, I can't recall offhand the difference in gas to stars fraction. I think it's higher for lower mass galaxies, but yeah.
I think Mike was next.
So we talked about this a little bit, but for the larger audience, can you tell us what would excite you about coming to Georgia State in terms of facilities, collaborations, student population?
Absolutely.
Which races?
Yes, I am very excited about running in Atlanta. In terms of collaborations, I'm really excited that there's so much expertise on measuring black hole masses here, and also AGN feedback and studying the impacts of AGN on their host galaxies. And the field of AGN in dwarf galaxies is sort of just starting to dig into the impact that the AGN may be able to have in terms of shutting off star formation in dwarf galaxies. So that's something I'm really interested in exploring. And obviously I care lots about measuring black hole masses in these systems. So I think that there's a lot of potential for great collaboration here. And it's really unique that Georgia State has so much great telescope access. So the ARC 3.5 meter would be a really great resource in terms of doing a lot of this follow-up work where we want to take spectra of something 20 years later and see how it's changed. So I think that would be a really great facility to have access to for this kind of work. Yeah.
How about in terms of the students or student population?
Yeah.
Pressure while they're all staring at you.
So I'm
The undergrad.
yeah. I've heard that there's a lot of undergrads who are really interested in doing research here. And something that I find really exciting is rabbit hole. And so having undergrads who could follow up on some of these interesting objects that come up in these huge data sets, I think would be really exciting. And there's lots of neat stuff in these really great data sets, and I would love to have a lot of undergrads involved in research, and it seems like that's something that Georgia State really encourages and cares a lot about. So I'm excited for that. Thanks.
And then Todd, did you have a question?
Yeah, if I understand what just happened here, you have tens of thousands of galaxy candidates, and then you whittle it down to 100 or so, and 1% of those you confirm are AGN, 1 or 2% kind of thing. So, big seeds or little seeds? How does it all end up?
Yeah, I think that this is suggestive of little seeds because we're finding that AGN and dwarf galaxies are not actually that uncommon, especially as compared to higher mass galaxies. And it's also exciting because I mentioned that there aren't many systems where we can do dynamical black hole detections at the low mass end. But there has been some recent work where they are looking at the few where we can try to do this work, and they're finding that something like 80% of them do have black holes. And so using these various different techniques, we're sort of coming to a consensus that at least down to these sort of stellar masses of 10 to the 9, black holes are not that rare in dwarf galaxies. They're just hard to find. And so I think that that is more consistent with a model where basically everything has a black hole. Yeah.
Small things run the universe.
Yes.
I had a different question, if I may, and that is, you're doing a ton of stuff. If you were a faculty member, you're going to have a ton of other stuff to do. So what's your top 3 that you would want to do?
Okay. So new.
What do you love the most?
Yeah. So my biggest question is trying to get a better handle on the occupation fraction, especially below 10 to the 9. So trying to use some of these new surveys, which have better sensitivity or different cadence to try to get a better grasp on the lowest mass end of the occupation fraction. Understanding the various selection effects in dwarf galaxies, so comparing AGN and dwarf galaxies selected through different techniques, and understanding why we select them with some and not others, is number 2. And then number 3 is these changing state AGN that I've become recently very fascinated with. Yeah, so I think those are probably my priorities. And I'd love to have grad students working on all those. Yeah. Yeah.
Justin?
Piggybacking off Tom's sort of first question, if you expect that these are created by the small seeds, would we expect to see any of that from sort of LIGO, or would we expect that all to sort of wash over us by now?
So LIGO is mostly sensitive to mergers of these stellar mass black holes. So the black holes that LIGO has detected are kind of like 30 to 80-ish solar masses. So LIGO isn't sensitive to the kinds of black holes that I'm looking at, but LISA will be. So LISA will probably have a lot more to say about intermediate mass black holes and things like that. So hopefully we'll see LISA fly, and that would be great for this.
Could you go back to your EP clock?
Yeah.
Any one of them.
Okay. There are many. Yeah. Okay, here we go. That's my favorite one.
So, I just want, do you have a redshift to all those points?
Mm-hmm.
What if you find the low redshift and AGN, the high redshift?
So these are all relatively nearby. So they're all within a redshift of about 0.05. So in that close a distance, you don't expect to see any redshift evolution. Yeah, so it's all a relatively nearby sample.
And the other thing is for those those points along the star formation band, the scattering could be caused by how they place the slit. Because in the couple of slides after it says if those are spatially resolved, depends on where they place those slits. Right?
Yes, but for these are all measurements made with a 3 arc-second fiber, so there shouldn't be as much dependent on, I mean, in some cases they might get the fiber really wrong, but in general for these, the fiber is basically covering the whole galaxy anyway. So, and that's part of why we think we may not be detecting them as AGN, is because the fiber is capturing the light from the entire galaxy. And so if there's strong star formation, it might be washing out the AGN signal.
Mike again.
I was just wondering, your techniques for defining little AGN, how that would compare with like deep Chandra surveys. Isn't that another way to define
Absolutely.
AGN?
Yeah, and so there are some Chandra observations in the archive for some of these that I've been digging into a little bit in the last couple of weeks, and we'll probably propose for Chandra observations of more of them this cycle. There was a really cool paper recently which looked at dwarf galaxies in the XMM archive, and they found a whole big sample of dwarf galaxies with bright X-ray emission that also fell in the star-forming region of the BPT diagram. So that's kind of a complementary angle, but definitely really valuable. Yeah, sometimes it does get messy because the X-ray emission from these can be at the level that you could get from X-ray binaries, and so you have to be careful about distinguishing between the two. But yeah, X-ray is definitely something that I've done a lot of work with in terms of confirming these and things like that.
Okay, we have time for one final question. If anybody has a burning remaining question they'd like to ask. I don't know. I suppose we'll let Todd.
Working with Kelly Cruz to this.
I had a couple of REU experiences as well, where one of them I got to work on planetary nebulae, and another one was working on AGN, and I enjoyed all of it studying brown dwarfs, but I was just called towards extragalactic astronomy.